welcome to the Geometrics channel. In this lesson, we will continue to investigate different types of angles found in circles, focusing today on angles formed by tangent and secant lines. Down in the description, you will find a link that will give you access to a free printable guided notes worksheet that will follow right along with this video. Check that out if you'd like to write some notes down as we go. Now, a couple of quick definitions before we dive right in here. So first of all, a secant line. A secant line is really just kind of an extension of a chord. If you remember, a chord in a circle is just a segment that has endpoints on the circle. A secant line is just the extension of that chord. So if you extend out your line, make it go infinitely in both directions. This is what we call a secant line. So a secant line is a line that intersects a circle in two distinct points. We also have something called a tangent line, which a tangent line is a line that intersects the circle in exactly one point. Okay, so the angles that we're going to talk about today are going to be created or formed by these types of lines on a circle. Okay, so we're going to start by taking a look at angles formed with two secant lines. So let's start with a circle here, and we're going to draw two secant lines that intersect inside the circle. So there's one, and there's the other. Now notice that these two secant lines don't necessarily go through the center of the circle. They could go through the center, but really I want angles that don't necessarily go through the center because I don't want to deal with central angles here. So we're looking at angles that are just kind of floating somewhere in between the edges of the circle. Now, when this happens, just like with any intersection of two lines, we create four angles. You can see we've got four angles in here. Now, in these four angles, we really only have two different angle measures, and all these angles are related. So we have two sets of vertical angles. So like this angle here and this angle here, those are vertical angles. Those are congruent, just like these two here are congruent as well. And then the relationship between adjacent angles, because they're both lying on straight lines, because we know a straight line is 180 degrees, any adjacent pair of angles are going to be supplementary. They're going to add up to 180. Okay, so all of these angles, if I know one of them, I can really get all of them. So when we find our angles today, keep that in mind. If we know one, we can really get all of them. Now, we'll just restart here. So when I take that situation where I draw my two secant lines that intersect, I'm going to put some points in here. So again, not necessarily at the center, somewhere in here, but just somewhere inside of the circle. I'm going to give some points here. This is A, B, C, and D. And we're going to we'll call this right here our angle in question. So this is angle 1 right there. Now, if you remember, we've talked about inscribed angles in the past, and inscribed angles are angles that have a vertex on the edge of the circle. And since we know quite a bit about inscribed angles, we're going to use those to kind of get what we're looking for. So what we're trying to do is we're trying to figure out a way to relate the angles that are created by those two intersections with the measures of the arcs that they intercept. Okay, so to do that, first thing we're going to do is we're going to draw an extra little chord here from A to D. Okay, so we're going to draw that extra chord from A to D. And when I do that, I've created a couple of inscribed angles. So you can see I've got an inscribed angle BDA. So that's an inscribed angle. The vertex is at D. And I've also got inscribed angle CAD. So a vertex at A, CAD. So I've got two inscribed angles, and those two inscribed angles intercept the two arcs CD and BA. So just kind of show you. So here's BDA. There's that inscribed angle. It intercepts this arc here, AB, and then CAD intercepts arc CD. Now, if you remember the inscribed angle theorem, we know that an inscribed angle is always half of the measure of the arc that it intercepts. Okay, so if I look at what we have here, I can say that the measure of angle BDA, okay, so the angle of measure BDA, so this purple inscribed angle right there, is going to be half of the measure of the arc that it intercepts. So that's arc AB. So measure of BDA is equal to half the measure of arc AB. Okay. And I also know with the other inscribed angle CAD, I know that's true as well with arc CD. So I can say it's also true that the measure of angle CAD is equal to half the measure of its intercepted arc, which is arc CD. Okay, so it's the inscribed angle theorem. We know that those arcs are going to be double the angle, or the angle is half of the arc. Okay, Okay, so we're going to hold on to this for a second as we kind of look inside here. So when we draw that secant line AD right here, we've created a little triangle in the middle. And in that triangle, angle 1 right up here is an exterior angle of that triangle. So it's not an interior angle, it's an exterior angle. An exterior angle is just an angle created when you extend out a side of the triangle. It's adjacent to one of the interior angles in there. But we have an exterior angles theorem, if you remember what that says. The exterior angles theorem says that an exterior angle of a triangle is equal to the sum of the two non-adjacent interior angles. Okay, so angle 1 right there is going to be equal to the sum of angle A and angle D, or my two inscribed angles CAD and BDA. Okay, so I know, just write it out here, I can say that angle 1, measure of angle 1, is equal to the measure of angle CAD plus the measure of angle BDA. Now, since we can substitute CAD with half of arc CD, we already had that from the Inscribed Angles theorem, we can put half CD in right here, just like we can put half AB in for the measure of angle BDA. So we can substitute what we have here into this little equation. So we're going to rewrite this as the measure of angle 1 is equal to, instead of measure of angle CAD, we're going to replace that with half of arc CD plus, and then we're going to substitute the measure of BDA with half of arc AB because they are equal. So now we have that the measure of angle 1, this angle right here, is equal to half of arc CD, which you can see is the arc that that angle actually intercepts, plus half of arc AB, which is the arc that its vertical angle intercepts. I can simplify just a little bit more by saying the measure of angle 1. If I pull out the half from each of these terms here, I can put the half out front and write this as the measure of angle 1 equals half of the sum of arc CD plus arc AB. Okay, so big picture, what this says is that the measure of an angle formed by two lines that intersect inside of the circle is equal to half of the sum of the two arcs that that angle intercepts. So angle 1 is equal to half the sum of this arc. Angle 1 intercepts this arc, and its vertical angles arc here and here. Okay, so an angle formed by two lines intersecting inside the circle is equal to half the sum of its two intersected arcs. Now, it's going to make a lot more sense when you put numbers in here, so I'll just give you a real quick little example, just so you can wrap your head around here. If I were to find angle X, I would need to know this arc measure and this arc measure, because the measure of that angle is half of the sum of these two arcs. And because I've made these numbers really easy, I can see 60 plus 40 is 100, and half of 100 is 50. So X in this case would be 50 degrees. All right. Now there's a similar relationship when we create angles outside the circle. So let's say we have a situation where we've got two secant lines, but this time they intersect not inside the circle but outside the circle. So there's where the two secant lines intersect. And I've got, let's say, two arc measurements, y and x, and now we're trying to find the measure of angle 1. Okay, so there's a similar relationship here. I'm not going to go ahead and prove it like I did the last one. The way you would prove it is similarly to how we proved the other one just a second ago. If I draw another segment right here, I've got a triangle where I can use exterior angles. I can kind of do it the same way. But the bottom line is, in this situation, I'll go ahead and give you the formula here, is that the measure of the angle, so the measure of angle 1, in this case, is equal to half the difference of the two arcs. We're going to start with y. Okay, so y and x are those two arcs. You got arc y right here, you got arc x right there. So this angle 1, when you extend out those secant lines, x and y are the two arcs that that angle intercepts. So that measure of angle 1 is going to be equal to half of the difference of these two arcs. So again, I would just take whatever y is minus whatever x is, take half of that value, and that's going to get me the measure of angle 1. Okay, now this situation right here where the lines cross outside the circle, you also might see it where maybe one of the lines is a tangent line and the other is a secant line, such as this. Okay, the same thing applies. So I've got that tangent point right there. I can still go about this the same way, where this would be arc y, this would be arc x in angle 1. So angle 1 is still going to be half the difference of those two arcs there. And also, I'll give you one more here, if it's two tangent lines, so two tangent lines intersect outside the circle, we only have two arcs. So there's arc y, there's arc x. Same idea. So the measure of angle 1 would be half of the difference of arc y and arc x. All right, so now that we have the two formulas, where if the lines cross inside the circle, it's half of the sum of the two arcs. If the lines cross outside the circle, like this situation, it's half the difference of the two arcs. Okay, so let's get into some examples here. We got our circle. I'm going to give us a diameter here to start, just to give us a place to kind of get our bearings about us. A couple of chords, and then some secant lines that intersect outside the circle. Okay, so the values we're going to get, we're going to say this is a 60-degree arc. We're going to go 70 degrees down here. This is going to be a 52-degree angle. This arc is missing, and this angle is missing. Okay, so we've got two variables to solve for. We've got an x and a y. X is an angle formed by two lines crossing inside the circle, and y is an arc. So I did give you a diameter. Now, anytime you have a diameter in a problem like this, it's probably a good place to start, just because you're going to have 180 degrees on both sides of the situation. So sometimes that can be helpful in finding missing pieces, and I can already see that this is going to be helpful for us right here. So I can see that this side of the circle, I've got three arcs, two of which I know, one of which I don't. I know the sum of all three has to be 180, so if I just take 180 minus 60 and 70, if I subtract those, I'm going to get the measure of this missing arc right there. So if you take 180 minus 60, that's 120, 120 minus 70, that's going to be 50 degrees. So I've got a 50-degree arc here, and how's that going to help me? Well, right there, for angle x, first theorem we talked about said if two secant lines, or in this case chords, intersect inside the circle, the measure of that angle is going to be equal to half the sum of the two arcs that it intercepts. Okay, so what two arcs am I talking about? Angle x is here, so if I extend it out to the endpoints of that circle, that's where angle x hits. So I know that this arc, this whole thing, because it is a semicircle, there's the diameter, I know that this whole thing is 180 degrees. Okay, so if I'm setting up my problem here, I know that the measure of the angle is equal to half the sum of the two arcs that it intercepts. So the first arc that it intercepts is the semicircle, that's 180 degrees. Okay, its vertical angle intercepts a 50-degree arc. So good thing we found that. We're going to need it first thing. So 50 degrees is the other arc. From here, just some simple arithmetic. I take half of 180 and 50, which 180 and 50 is 230. And then half of 230 is 115. Okay, so we've got angle x is 115 degrees. Okay, so if we move on to angle y. Now angle y, or arc y I should say, arc y is one of the intercepted arcs from this angle out here outside of the circle. So that 52-degree angle, which is formed by two secant lines intersecting outside the circle, our formula said that that angle is equal to half of the difference of the two arcs that it cuts. So if I look at this angle, so the 52-degree angle goes from here to here. The two arcs that it intercepts would be arc y, and then at the end points out here would be this. Now we know what that is. This is a semicircle. So my outside arc here is 180 degrees. My inside arc here is what is missing, so I can use this to set up my equation. So again, the measure of the angle, in this case I know what it is, 52 degrees, is equal to half the difference of the two arcs that angle cuts through. So the outside arc here, because it's half the circle, or 60 plus 50 plus 70, that's 180 degrees, minus the inside arc, which is what we're trying to find. Okay, so with this setup, it's not quite as straightforward as this one since we had the variable isolated already. This time we're gonna have to do just a little bit of algebra to get what we need, but no big deal, we can get it done. So first of all, we notice that this side, we've got this half in front. I could distribute the half in to make this 90 and half y. I'm just gonna go ahead and multiply both sides of this equation by 2. I'm gonna start there just to get rid of that half right off the bat. So I'm gonna multiply both sides by 2. I've got 2 times 52, and 2 times 52 is 104. Now on this side, since that half and 2 is just 1, I can lose the parentheses there. I've got 180 minus y. Go ahead and isolate the variable. I'm going to subtract 180 from both sides, which is going to leave me with a negative 76, which is equal to, don't lose your negative there, negative y. And if negative y is negative 76, I know positive y is just 76, or I could divide both sides by negative 1. It's just going to get rid of that negative for me. So I've got y is equal to 76 degrees. All right, let's try another one. Okay, we're going to get a tangent line this time. And go chord right there. Okay, so we're going to get an 85-degree arc. We'll call this a 30-degree arc. This is going to be 116. This one is 72. And we'll say this arc x, angle there is y, and we'll get these two as well, w and z. Okay, so w, x, y, and z, those are the angles and arcs that we're looking for here in this case. Okay, so again, a lot to wade through, a lot of angles, a lot of arcs. Okay, so the best place to start is with, the lowest hanging fruit that you can find. Best place, again, half circles are 180, whole circles are 360. If you can get any information based on those two facts, I'd probably start there. So that's what I see. First of all, I can see I've got 1, 2, 3, 4, 5 arcs around the outside of the circle, and only one of which is missing. So I'm going to take 360, and I'm going to subtract out the other 4 arcs from that total. So if I take 85 plus 30 plus 72 plus 116, add all those together, you get 303. And if I take 360 minus 303, that's going to get 57. Okay, so 57 degrees is my fifth angle, that is x right there. So this is a 57 degree arc. Go ahead and write that over here, x 57. All right. So next, we got a couple different ways we can go. I'm going to start inside here. From the first theorem, we know that two lines intersecting inside the circle, the measure of that angle is half of the sum of the two arcs that intercept. So looking at angle W intercepts this 72 degree arc. Its vertical angle intercepts this 30 degree arc. So W is half the sum of those two. So W is equal to half of 72 plus 30. And if you add 72 and 30, you get 102, half of 102 is 51. So W, 51 degrees. With angle Z, I could do the same thing. I've got the arc it intercepts is 85. The arc its vertical angle intercepts is the 116 and the 57. I could do that again, but that's more work than I have to do because I've got a linear pair. Two angles right next to each other on a straight line do have to add up to 180 degrees. So if I take 180 minus the 51, that's going to get me angle Z, And 180 minus 51 is 129 degrees. So Z is 129. Okay, last one we got here is angle Y. Angle Y is an angle formed by a tangent line and a secant line intersecting outside the circle. So again, the formula for that is that angle is half the difference of the two arcs that intercepts. So again, extending out that angle, we're going here to here, the endpoints being there. So I've got outside arc, which is all this, 116 plus 30, which is 146. And then the inside arc is 57. So Y, right here, Y is equal to half the difference of those two. So 116, 130 is 146, minus the inside arc 57, which is half of, it's going to be 89, and half of 89 is 44 and a half. Okay, don't freak out if you get a decimal or a fractional degree measure. It's usually fine. Don't just think because you have a decimal it's probably wrong. It doesn't necessarily mean it's wrong. It just means you divided an odd number by 2, you get a half. Alright, so that's it for that one. So that one, even though I didn't have a diameter here, I can use that fact 360 all the way around, kind of got me started there. And then you're just kind of searching for those situations, in this case, where the lines cross inside the circle, or if the lines cross outside the circle. Let's do one more. So the first two so far have been kind of involved, had a lot of lines and angles and arcs and everything. Let's do one that maybe looks easy, but might not be as easy as you think. So this time, we're just going to go with 2 tangent lines. That's it. So tangent point here and here. I've got a 40-degree angle, and that's all I'm going to give you. So we're going to look for this arc here, this arc here. All right, so less going on, but also less information that we know. So we've got an angle formed by 2 tangent lines intersecting outside the circle. The 2 arcs that that angle intercepts are both missing. Okay, so that's kind of a problem. What I want to do though is I'm just going to use the equation. I'm just going to write out what I know and kind of see where we can go from there. So I know the formula says that the measure of this kind of an angle is equal to half of the difference of those 2 arcs. Okay, so in this case we just have the 2 arcs. We've got the outside arc here, and then we've got the inside arc here, arc X. So I know 40 is half the difference of those 2. So I'm going to write it as half of Y minus X. So there's my equation. You might think, well, that's impossible to solve because I have 2 variables. I can't solve for either one. So what I need to do is I need to somehow relate one of these variables or write it in relation to the other. So what do I mean by that? How can I relate arc X and arc Y? What do I know about those 2? Specifically, what do I know about the sum of those 2? Okay, together, those 2 arcs make up the entire circle. And what I mean by that is that arc X plus arc Y, if I add those 2 arcs together, what does it have to be? It's an entire circle. It's 360 degrees. All right, so if I know that those 2 angles together make 360, what I can do is I can solve this little equation for one of the 2 variables. Let's just solve for Y. If I were to solve this equation for Y, I can just subtract an X from both sides. If I subtract X from both sides, I'll end up with Y equals 360 minus X. Okay, so Y equals 360 minus X. Now that I have this relationship, I can replace or substitute 360 minus X anywhere I see a Y, right there. And what that does is that gives me an equation that is only in terms of one variable, and then I can solve for X. So let's replace Y with 360 minus X and go from there. Usually I would put this in parentheses as I go up here, but I don't really have to in this case because I'm not multiplying or dividing anything. It's just addition and subtraction. So I'm going to just go ahead and put it in there. Okay, so here's my equation. We can clean it up a little bit. On that last example, I went ahead and multiplied both sides by 2 to kind of get rid of that half. I'm going to go ahead and do that as well. Since I've got half times all this extra stuff, I can multiply both sides by 2 to get rid of that. So I've got 40 times 2 is 80. equals, and then I've got 360 minus x, that's really negative 1x minus 1x, so I can write that as minus 2x. Okay, next I'm going to go ahead and subtract this 360 from both sides. So I'll isolate my variable negative 2x, 80 minus 360, that's going to give me a negative 280. Last step here, divide both sides by negative 2, and I will get my x. So I've got x equals negative 280 divided by negative 2, that's going to be a positive 140. All right, so I've got x is 140 degrees. And then the quickest way to get angle y, since again, those two together make an entire circle, 140 plus what gets me to 360. 360 minus the 140 gets me angle y, which is going to be 220. Okay, so that'll do it for these types of angle measures inside and outside of circles. If this was helpful for you at all, please go ahead and give this a thumbs up. It would help me out a lot and help the channel out a lot. If you'd like to see more videos just like this one, please feel free to subscribe to the Geomastic channel. Thanks as always for watching. We'll see you next time.